Thank you very much, and thank you very much to the organizers for inviting me for this special occasion. And I'm very happy that I can participate in the celebration of Bill's achievements. I remember very well when I met Bill. This was in the heydays of Bergman Spaces. So there was a conference in Mount Holyoke College. And Bill very kindly drove me back from there to New York City, I think. Very nice ride with him. And we have met over the years since then. So I should also apologize to some people in the audience because I will talk about things you have heard me talk about before. And I cannot promise that this is the last time because this is very much work in progress. So I'm afraid you may have to suffer another time. So there is a paper that was published this year with this team of authors, and there is a new team of authors working on something right now. So I will talk, basically tell you about this, the state of affairs. So yeah, let's see now. So where are we? This is super classical. We are dealing with the Paley Wiener spaces, PWP. Consists of P is some number between 0 and infinity, and PWP consists of entire functions of exponential type at most pi that are integrable along the real line. Alternatively, we can think of them as functions whose Fourier transform, defined in this way, is supported on the interval from minus pi to pi. If p is less than 2 or less than or equal to 2, these are decent functions, and otherwise they are distributions. And of course, the smaller p is, the smoother, that requires more decay, and so the Fourier transform is the smoother the Fourier transform is. And the problem is the following. We define the norm of point evaluation at 0. We could take any other point because the space is translation invariant. So we want to know what the size of this number is, Cp. Another way to define this Cp is to say that this is we want to find the function that minimizes the norm or the quasi-norm when we fix the value at 0 to be 1. It's not hard to see that extremal functions exist for all p between 0 and infinity. These functions are real on the real line, and they have only real zeros. That requires a small argument, but it's not hard to see that all zeros have to be real. And when p is larger than or equal to 1, we can prove uniqueness of the extremal function. For p strictly between 1 and infinity, this is just by strict convexity, and for p equals 1, it requires a little more, but we can prove that. But I'm totally convinced that the extremal functions are unique also when p is less than 1, but we are unable to prove that. So anyway, for p larger than or equal to 1, the unique solution, then, as a consequence of what I just said, it takes this particular form. We can write it as an infinite product. I forgot to say that since it is unique, it also has to be even, because phi of minus x would also be an extremal function, and so then the only possibility is that it's even. So since these functions are even, they can be written up in this way in terms of the zeros, an infinite product of the zeros, the positive zeros. When p is 2, we are in a trivial situation. Then C2 is 1, and phi 2 is the sinc function, sine x over x, right? Sine of x over x. And the zeros are then the non-zero integers. So I think of this problem really as a basic problem in time frequency analysis. When p becomes smaller, it requires more decay of the function, smoother Fourier transform. So there is an interplay here reflected in how this Cp differs with p. So what do we want to know? Well, as I've just said, we want to compute Cp. And we would also like to identify the associated extremal functions. Okay? And then associated with that, we also want to know how Cp varies with p, as I just said, and also how the zeros vary with p. And then it would be nice also to know the asymptotics. What happens when p goes to 0? What happens when p goes to infinity? So the third problem was more or less solved in the first paper we wrote. The behavior of Cp. I couldn't say so much about the extremal function, but at least Cp, we can say how it behaves when we approach 0 and infinity. But unfortunately, the situation is that we have more conjectures than results regarding the two first points, more conjectures and a number of authors, as someone said in the morning. So there are plenty of conjectures and few results. So what I will do now is to give a brief, incomplete account of what we believe is true and what we know. And then I will present some progress on the second most accessible case. P equals 2 is completely accessible, we understand everything, but p equals 1 is a special case that, for which we have some tools. So I will tell you about that now. And really, I have to say, what is emerging in this situation is really a remarkable structure, so of which much remains to be understood. Okay, so let me give you a brief history. So this problem of computing Cp was proposed by Levin and Lubinsky in 2015, who identified 1 over Cp as scaling limits certain Christoffel functions. I mean, this problem could have been posed 100 years ago. I mean, it's super classical, but for some reason, it arose in 2015. And then, as regards p equals 1, there has been quite a bit of activity. These are works that I'm aware of. There could be others. So there is a paper by these three guys in 89, where the problem is first formulated, or well, indirectly. And then there is a very interesting paper, which I will speak a lot about, by Hermander and Bernhardsson in 1993. Then there are some contributions from there are two papers by Russians. And then we have Andreev, Konyagin, Popov, and then Gorbachev. And then in 2019, there is a paper by Carneiro, Milinovic, and Sandara Raja, who really care about estimation of prime gaps, but it turns out that this extremal function for p equals 1 is actually quite useful in this context. As regards Hermander and Bernhardsson, and I should probably also say Bhatia, Davis, and Kusis, is they started really from something else, and it's more or less the same. But let me say exactly what Hermander and Bernhardsson were interested in. They were interested in finding the best constant in an inequality of this form, which they term Bohr inequality, because Bohr did work in 1 dimension, and they wanted to do similar things in 2 dimensions. So what do we have here? We have U is a tempered distribution on R2, with a gradient bounded, and with U hat 0 in a disk around 0 of the radius lambda. And then you have an inequality of this form, so the gradient the sup of the gradient will dominate the sup of u, and the precise constant here will then emerge as our constant C1, well, with this extra factor 2 over pi. And then what Hermander and Bernhardsson do is to transform the problem of computing this C to the problem that with Paley Wiener PW1. I mean, there is a radial symmetry here that helps you get to that problem. So there have been various reasons that people have been interested specifically in the case p equals 1. Hermander and Bernhardsson is a remarkable work. They were able to really get a pretty good grip on what C1 is. Not bad. But there are some shortcomings, as I will explain. So I will come to that later and explain a bit about what they did. Okay, so let me just say a few words about other p's than 1. I will concentrate on p equals 1 later in most of the talk, but let me just mention a problem that I find quite interesting. It is a conjecture that the function Cp over p should be strictly decreasing on the interval on the real line. I can only prove this for p equals 2. So why should we believe in this conjecture? Well, there is something which I call the power trick, which allows you to see that at least it decays along a certain sequence of points. Namely, if there is a positive integer such that q and p are related in this way, q is k times p, then we have a domination like this. And this you see just by taking a power. Okay, so you take an f in pwq, you take the qth power, then the function is of exponential type k pi. Okay, so what you do is you divide by k in the argument, and then you get back to a function of type pi. Okay, and then you just start computing and see that your f at 0 raised to the power q is equal to the new function g raised to the power at 0 raised to the power p, and then you just make a change of variables in the integral, and out comes the k in front of the estimate. And so you see that you got exactly what you wanted, this bound, which is the same as the bound upstairs because of this relation. So this is one good reason to believe in the conjecture, and then I will tell you another good reason. Namely, for a reason that I'm not really able to explain very well, we believe, or we are sure, that the extremal function is extremely close to this function. So what is this? Well, actually, it's will be we see below here that you can express this in terms of it's actually a Bessel function up to a factor of the first kind. So, well, anyway, we believe that this function is very close to the extremal function, and this was also what the starting point for Hermander and Bernhardsson. So they were also aware of this fact. So in their case, this was just the power here would be, since p is 1, it would just be 1. And what they did was to add powers of this thing in the brackets, 1 minus xi squared over pi squared. So they added some coefficients times powers, higher powers of this thing, and used Newton's method to approximate. And they were then able to get what you saw on the first one of the first slides. So anyway, this then in this situation, for which we know basically everything. It only differs in the 4th decimal place from the extremal function, from the true value. Sorry, from the true value. So anyway, let me illustrate what we know between 1 and 4. So the gray line here is if related to p equals 2, what we get from the power trig. So if the power trig was an identity, we would have the gray line all the way, right? It's the line p over 2. The blue line, the blue curve, is what we get from these functions that I showed you on the previous slide, and this we believe is up to let's say the 3rd or 4th decimal, the truth. So think of the blue line as the true value, and then between 2 and 4 we can actually do something, and what you see there is work that will be presented on Wednesday by Sara Instanes. So this is a teaser for that talk. So this red line is an improvement over what we did in our paper, this 24 paper that I have been told you about. So this is the situation, and let me also mention very briefly that this curve, which you saw on the previous slide, oops, what happened? Now I'm getting too far. Okay, I should go back, right? So what happens when you go to 0 and what happens when you go to infinity? So think of the blue line as the truth. So what we say here is that, okay, the line will differ from the straight line, and it will actually behave like square root p when we go to infinity. So this is a precise estimation here. While when we go to 0, actually we stay pretty close to the gray line, 2 over p. We do not know the exact constant. There is a limit when p goes to 0, and well, I don't know what this constant is, but it lies in this interval. So we wrote this long paper, and there are, I'm ashamed to say, there are 15 conjectures in that paper. I really hope that some of them will be solved one day. I think everything here is interesting, but some of the problems are not so easy, I guess. So I don't know, we will see. But anyway, this is the situation, and let me now go to a very important point, which I think was pretty much covered by Dima's lecture. Oh, sorry. So this is the usual extremal, the variational argument you use when you have an extremal problem in LP. So a standard variational argument leads you to a reproducing formula which looks like this. So when p is 2, of course this nominator will go away, and you see in front of you the usual reproducing formula for the Paley-Wiener Hilbert space. So it embodies this fact that the zinc kernel is the reproducing kernel of the Hilbert space. And then we come to p equals 1, and the virtue of p equals 1 is that this formula simplifies a lot, because actually this ratio, well, not the ratio, but the nominator times phi here, it will just take the values plus minus 1, right? Phi of x over the modulus of phi x. So it's a much simpler formula. And this is what can, one of the things that help us understand this case. So now, from now on, I will speak about p equals 1. So it's when you see the precision of Hermander and Wernason, you may be surprised to hear that they were actually able to say essentially nothing about the extremal function. So they had a very, this numerics or the algorithm with Newton's method, it worked very well. They had very good convergence, but they couldn't justify it. So basically the only thing they could prove about the zeros was that they were separated. Okay, so this is what I say here, that well, we order them by increasing magnitude, and this is a strictly increasing sequence. On the other hand, their works very much suggest that tau n should be close to n plus a half. So this brings me to the other virtue of the case p equals 1. We have this plus minus 1 in the reproducing formula. This is very useful. And the other thing is that if you think about the sequence n plus a half, it's actually an arithmetic progression. Okay, so you have zeros on both sides, or points on each side of 0, but they match, so that you have in fact an arithmetic progression. And this is very useful. So there is a periodicity in this problem that you wouldn't have for other p's, except p equals 2. So for the rest of the talk, what I will say is based on work in progress with both Radchenko, Ortega-Cerdà, and Radchenko, Danilo Radchenko. Okay, so now I will get to some small computations. So let us take phi, a function in the Paley space with zeros, with the same kind of function that the extremal functions, with zeros on both sides, symmetric about 0. So a function of this form. And let us then introduce this function. This is actually the kind of function you saw in the reproducing kernel. Okay, but now phi is any function of this sort. What do? We want to play with this arithmetic progression, n plus a half. Okay, so for that reason, we introduce this function. So this is a similar kind of function with the same absolute value, because we scale by the same number, the reciprocal of the L1 norm. But now we have the sign changes at the zeros of the cosine function. Okay? And the idea is that actually, except for the first 0 at the half, these two guys should be really close to each other. Okay? Because the one changes sign at tau n and the other at n plus a half. Right? And if they are close, well, they should be very close to each other. But then you observe a very nice feature of, if you take the Fourier transform of this guy and sit down and do your computations, you will see that the Fourier transform is actually 0 on the open interval from minus pi to pi. Okay? Well, that's a very good thing, because this means that we can throw it in and it doesn't affect the computations. So we can subtract it and it doesn't do, so to speak, any harm. And this is the reason we're able to get to the following lemma. So we have phi as described here, and we suppose that we have that the sequence of zeros is so close to the n plus a half sequence that this thing is in little l2. Okay? Then we take the convolution of the difference between phi and psi with the sinc kernel, the reproducing kernel of the Paley-Wiener PW2. This is in P. This thing is in the Hilbert space, and then we can get an upper and lower bound for C1 in this way. The lower bound is trivial, because I took some function. I would get an equality if I took the extremal function, but for any other function, this number would be smaller. The reciprocal of the norm will be smaller, so this thing is a triviality. But the interesting part is the upper bound, because what you realize is that, okay, if you hit the extremal function, this should be 0. And that gives you an equation for finding the extremal function. So let's see now. I have a proof of this lemma, but I'm not sure. Immediately after lunch, and people are maybe sleepy. Maybe I should skip it. It's not very hard, but it's playing with this. With I told you that this function psi that we threw in, it vanishes on minus pi pi, so we can play with it and throw it in at the right place, and then, well, doing a few small things, we arrive at this lemma. You believe me, I hope. I think I'll skip the details. So let's see how we can use it. Okay. So now the thing is that if we are able to find phi with this in L2, and so that the thing that you saw inside of the L infinity norm is 0, we actually know by this lemma that the phi we have in front of us is phi 1. So our job is therefore to find this L2 solution to this equation where you have the unknowns are the delta n. So what I have done now is to rewrite, okay, so I should explain this. This equation, if I spell out what it means, remember that phi 2 is the sinc function. Okay, so you have the sinc function here, and also remember that we divided to define capital phi, we divided by the norm. And suppose you hit the extremal function, then in your equation you would get this number C1. And then since you have, well, the 2 just comes from the fact that we have something from the negative side and something from the positive side. So since it's an even function, I can only do this, it's enough to do things on the positive axis, so that's why I get the factor 2. Okay, so then, and then you take a look at this convolution, and you remember that phi and psi, they should be very close, except that this guy with the cosine, it also has a sign change at a half. So that's why you get the first integral here, because of the first sign change of the cosine function. And the rest is just this discrepancy between the zeros of the cosine function and the zeros of our guy, and we call delta n the difference. I think I hope I put it somewhere, the delta n. I should have had it in my plan was to have it in the headline, but I forgot. But I hope you understand that delta n, I should write it maybe on the blackboard. Delta n is n plus a half minus tau n, so the difference between the zeros. So this is just a translation of this, as I said, of this equation to make it very explicit. So then this equation you should think of as an equation for the delta n's. And what's the best way to treat it? Well, it turns out that is a pretty good idea. Why in principle, well, it's actually should hold for all real y. But what you can do is to choose a good sequence. And a good sequence turns out to be the half integers again. And the reason the half integers are good is, I've tried to explain it here. So well, then the equation becomes this equation. And the thing is that there is one term that will give a significant contribution, and that's the term when n is equal to k, because then no, sorry, it's, yes. So if n is equal to k, this guy will be essentially 1. It's clear? It will be essentially 1. So that will give you delta k. While all the rest of the terms will be super small in the sense that it will be order power of 3 of the delta, whatever delta you're dealing with. And this means that if you then take another point of view, that you take out this delta, and then you rewrite your equation in this way. So the deltas that you get out, you put on the left-hand side. Then you have a constant term w, and then you have a nonlinear operator acting on delta. And this is super small, actually, super small. And then when when I saw this, I have some good friends who know fixed point theorems, and this smells fixed point theorem of this, and actually this is how to do it. So you write now, you introduce this operator w minus rx, and we want to verify that this operator has a fixed point. And the best way to do it, I think, is well, we have a paper out on the archive where we do this in a Hilbert space, but it's better to do it in this way, and weighted L infinity space. If you look at the previous slide, I don't expect you saw that it's natural to have this weight on it, but believe me, the right thing to do is to look at this weighted space. So you put the weight n plus a half as a weight in the norm. So it's a weighted L infinity sequence space, and then you figure out by doing some computations that actually a good set to use is this set of sequences where the double omega n lies in this interval. And it turns out that on this set, k acts as you want it to do. It maps k into itself, and it is a very good contraction. Very good contraction. And the reason it is a contraction is that this extra term with the extra nonlinear term is basically order 3, so it's really small. So then by Banach fifth point theorem, our sequence lies in K, and we have verified this thing that the zeros are indeed very close to the sequence n plus a half, which was really in the air in Hermander and Bernhardsson's paper. Okay, that's fine and good, but then what else is there to do? Well, a lot more, I'm pretty sure. So what we can prove is that these zeros, they can actually be expanded in odd powers, negative powers of n plus a half. And numerics indicate that these a's decay very well. They decay like 1/4 to the j. But this I cannot prove for the moment. And then we come to the work of Hermander and Bernhardsson, who say explicitly that they have super good convergence. And also there we can see that, yes, indeed, if we go to the other side of the Fourier transform, we can also verify that this is actually, I mentioned to you how they did their work, and if you now take higher powers of this 1 minus psi squared over pi squared, there is strong, what we see is that what actually Hermander and Bernhardsson did was to compute the first part of what appears to be a very quickly convergent expansion of of the Fourier transform of the extremal function. We have in this new team, there is a lot of incredible numerical competence in the team. There are people there who are able to generate conjectures that seem, for the moment, completely out of reach. But there is a structure here which is something I didn't expect to see. Specifically for the case p equals 1, I think we can put our hands on it. And then what I hope is that this could be a guide to understand other p's that for the moment are less accessible. The third most accessible case is probably p equals 4, because you can relate it to convolutions on the Fourier side. And if you could understand this convolution problem, you have a good chance to understand p equals 4. So there are other cases that could be approachable. But I think that this phenomenon that you see that Hermander and Bernhardsson were able to, or what they started, most likely you would have the same for all p, but then with a different power of this guy, corresponding to what you saw in the slide where I told you about these functions coming from the Bessel functions. And that's another very curious thing, that you have this, that the functions are so close to Bessel, but not quite. They're not quite Bessel. So there's a little bit off. This is also another thing which we really do not understand. So lots of mysteries remaining, and that's pretty much what I wanted to say. So let me just say happy 60th birthday, Bill.
Thank you very much for this very nice talk. Are there comments, questions?
This expansion you had on the last
Yeah.
slide, so I mean, if these coefficients really decay like
They go extremely fast to zero.
So then they're the coefficients of some analytic function.
Oh, definitely more. It's better than it's an entire function actually.
Yeah, and so then that function has some kind of magic property then.
Most likely, most likely. There are some treasures to be found here. I'm convinced.
So is there any hint about what any other way to find this function or something?
Not that function. I'm not aware of that. But we see some. Well, we see something, but it's too early to say exactly what we see. Yeah.
Implicitly, your tau n should depend on p. Is there any?
It depends on p, of course.
Well, it does, but I mean, is there?
Yeah.
Clear,
It depends on p is maybe you can help me, Sarah, but it's n plus, let's see, it's p over 2, I think. No, wait a second. Sorry, minus 1? Or the other way around? Minus 1 plus, minus 1 plus pi over t, p over 2. Sorry?
I'm not completely sure, but I think you can get 2 over p and not p over 2.
2 over p. But this couldn't be, plus a half. Plus
I'm not sure.
2 over p, yeah, this makes sense. Minus a half. Yeah, that's it, yeah. So this is, so for given p, zeros are very close to that. And this corresponds to the zeros of the Bessel function. You will see if you, yeah. But what we know about the zeros in general is ridiculous compared to the precision we expect to see. So, I mean, there is a long way to go. Yeah.
More questions or remarks? It's not the case, so thank you again.